Hello everybody. This week we're going to be exploring Newton's second law. So make sure you've logged into Pivot Interactives, and we're going to be doing Newton's second law experiment. So let's take a look at this. So the objectives here are to calculate acceleration from displacement and time. So we will be doing that. So that relies on stuff we've done the first several weeks of class. And from the acceleration, we'll be able to look at the relationship between net force, mass, and acceleration. So we'll do a couple of different sets of data. The first one is to find a relationship between force and acceleration for a given mass. So we'll leave the mass the same, play around with the force, and see what happens to the acceleration. And then the second one, we will leave the force the same and play around with the mass and acceleration and see how those are related to each other. Okay, so we'll be using this turbine-powered glider in this lab. Okay, so make sure you watch the video and we'll take a look at it in just a minute. Read the following description that will help you understand what you're watching. So essentially you have an overhead view of what's going on. So here's the overhead top view, and then we also have the side view. So this is an air track. We're assuming that there's no friction. So this air track has little holes in it, air is blown up through the track, and the cart here floats on the air. Now in reality there is some friction between the cart and the track, and there's also some air resistance. So this is a turbine here. Initially it's connected by a spring, and once we disconnect the spring from the cart here, the cart will go down the track. So let's actually take a look at it here. And right now it's set up at 800 grams, so that's 0.8 kilograms, and fan force 3. This doesn't mean 3 newtons, that's just the third setting. There is a way to measure the force, and we'll see what that is in just a minute. So here's play. Okay, and there the cart accelerates down the track. So we just want to look at the motion while it's accelerating most of it. Let me reset this. And you can play it frame by frame. Let me get it going here a little bit. Pause, and I can move it frame by frame. Okay. Now if you notice, the spring is stretched. I can go back. And I'm going back, if you can notice that, to the point before we actually turn this on. Okay? A little bit farther back. So here the spring is at its relaxed length. The fan hasn't been turned on yet. Just to let you know. And then once you actually turn the fan on, the spring stretches. You can measure how much force is being exerted by the spring by knowing how much it's actually stretched. So in the toolbox, we've got a few things here. Here is a ruler of sorts that has force on it. And this force can tell you how much the spring force is. So if you go back to the point where it's relaxed, set that as the 0 Newton part, and then actually let's just do it. Probably easier to see it than me talk about it. Let me go back to the relaxed length before it's actually turned on. Okay, still turned on. Okay, so this is where it's not stretched at all. I can pick whatever point I want to. I'm going to do the front of the spring. And then go to the point where it actually is turned on, and you'll see that the spring is stretched. Okay. So you get an idea how much force we have, right? The spring force is proportional to how much this is stretched. So right now the way I'm looking at it is, once you turn the fan on, it's 1.5 newtons. So the fan is interacting with the air. The air pushes back on the fan. This is the force of the fan to the right being balanced by the spring force back to the left. And then once you cut the cord here, the fan is still on, so you still have that amount of force. Okay, so that's how you can get the force, by measuring it that way. Again, it says fan force 3, but that doesn't mean 3 newtons. It's whatever this turns out to be. And you can change it by clicking here. Okay, just wanted to kind of show you how it works. You also have some other tools here. You can get rid of this if you want to. You can bring in an actual ruler this way. So part of the lab is to measure the acceleration, and that's after, again, after this has been cut. Just advancing it forward a little bit. We're going to be calculating the acceleration from knowing how long something takes and the displacement. Okay. Let me go a little bit farther. I want this to, the string to be cut. Da-da-da-da. Almost there. I guess I should have just hit play and then paused it when it got close, but we're almost there. Okay, so now it's cut. I can take the ruler, put it on the front edge or wherever you want to. Maybe you prefer it to be up here. Maybe you want it on the front edge, wherever you can see the best. I'm actually going to try this point. You don't have to do that again. You do it however you want to. So at a certain amount of time, at 3.2167 seconds, I'm located at 0. And then I want to, from the displacement and the time, I can calculate the acceleration. And that's where it's first starting, so the initial speed is 0. Let me make sure that's where it's first starting, because I'm using the fact that the initial speed is 0. Let me back it up a little bit. I think that's pretty good, actually. You can tell 3 frames it didn't really even move. Okay, so at 3.1917 seconds, we're located at 0. That's where it first starts moving. And now I want to get to a nice convenient spot and see how long that takes. So that's my initial time coordinate. And we'll just go ahead a little bit. Let me hit. And you want to stop it before the person interacts with it. So to me, it's gone about 0.71 meters in whatever that time was. You'd have to write down the first time, the second time. So again, initial speed 0, displacement, you measure that, get the time increment, not the time coordinate, the increment, which means this time minus the time where it started. You can calculate the acceleration. So these 3 quantities you'll need for this lab. The mass is just given over here. The force you get from using the force meter stick up here, seeing how much it stretched before you actually let it go. And the acceleration you'll have to calculate by knowing the displacement and the time. And we're assuming that we're starting from rest. Okay, excellent. So keep that in mind as you go through the lab. Acceleration and glider, all these different sections that you have. Multiple choice. So make sure you read it carefully, watch the video, and answer these questions. For this part, calculate the acceleration. So again, it's multiple choice. Just keep in mind, which kinematics equation are you going to use? So you know delta x, you know the time, you know the initial speed is 0. From that, you can calculate the acceleration. Okay, now the next part deals with forces exerted, and the glider. You probably noticed that you can vary the fan force in the video. And a few questions about this. Just keep in mind the fan pushes on the air pushes back on the fan. That's really what's propelling the cart down the track. So you're going to read through this carefully. And then here's a little bit with free body diagrams. So this is advance the video until just after the ribbon is cut. What are the actual forces on the cart after the ribbon is cut? Okay, so think about that carefully. Another multiple choice scenario here. Okay, measure the force. All right, excellent. Experimental questions and procedure. So here's a little bit to think about before you actually conduct the experiment. So before you begin, write a hypothesis for each operational question. And how does the acceleration depend on the force of the fan for a given mass? And how does the acceleration of the glider depend on the mass of the glider for a given force? We're doing both of those scenarios. So make sure you write it in this format here. Collecting and analyzing data. Okay, so here's the video again you'll see. So remember how these things work. You can add columns. You're going to have to add some columns to this. So we're going to have a given mass, and we're going to change the force. So you'll have to have a column that has force on it. You'll have to have a column that has displacement. You'll have to have a column that has time, right? Because because of the displacement at the time, you can calculate the acceleration. So you could actually then include an acceleration column. So just as to summarize, you'll have one with the force, you'll have a displacement and a time, and then you'll have a column for the acceleration. Now the acceleration column, you can calculate that one by hand, or there's a little hint here. You can, if you clicked on the three dots, by the three dots it means here, you can do change column formula, and you could do something like, whatever formula that you come up with to calculate the acceleration, or you could just do it by hand. Okay, and then we want to plot our data here. So on the vertical axis you'll have force, and on the horizontal axis you'll have acceleration. So from Newton's second law you should be able to tell what the slope actually represents. Okay, and then the equation of the line should be something like this. I'll have to go back through and correct that before you actually see it. There's an extra line in here that you don't need. Okay, and good. And then the second part is also here. So for this data table, we're going to check out how the acceleration depends on the mass. So in this part, we're going to leave the force the same and change the mass, and then see what happens to the acceleration. So pick a force that gives you nice constant acceleration, and go through, and you'll have a similar data table. You'll have an additional column though. You'll have a column of 1 over m. So 1 over m just means 1 divided by the mass. So what we're going to actually be plotting is the horizontal axis should have 1 over m. Okay? And the vertical axis should have the acceleration. So same thing, you'll need a displacement column, a time column, a calculated acceleration column. Now we're keeping the force the same, so you don't need a force column this time. But you will need a mass column, and you'll need a 1 over mass column. Okay? If you think about Newton's second law, you'll see why we're plotting 1 over m, like F is equal to ma. So think about that. And then again, create your graph here, and put the function of the line on for this graph and the other graph. Okay, and then finally, another question here, some general conclusions. How do you account for the % difference of your graph? Don't just say there's human error. You have to be more specific. How would you make the graph more accurate? What would you change if this were your job and it depended on it? You're working for NASA. What would you change? Okay, and what assumptions did you make that maybe weren't actually true? That sort of thing. And then conclusion, describe, summarize the relationship between net force and acceleration for a specific mass. This refers to the first graph you made, and then this refers to the second graph you made. Okay, and you have until Sunday, October 4th to do this. Okay, so a little bit more time with this one. You have the remainder of this week and then also next week. Okay, good luck. Any questions, just let us know, and we'll talk to you soon. Bye-bye.